All right, last time we went over some very basic database definitions. To reiterate, we went over what a table is. And the table is information about one entity. An entity is typically going to be a noun in our business problem or organizational problem. Person, place, or thing. If we think of in a college's database, students, rooms, instructors, maybe, equipment, all those things could likely be tables. We talked about rows in a database. A row is all the information about one member of the entity. So in the student table, there'd be a row for each of you. And sometimes it's called a record too, sort of synonymous. Columns are the individual pieces of data. So your first name, last name, address, city, state, zip, those kinds of things would be columns in the database. One of the key things we didn't define, though, I don't think, is the database itself. And database is sort of shorthand for relational database, because most of the databases that we're interested in are what are called relational databases. And you can think of a relational database as being a collection of tables and their relationships. Now, the relationships in databases are actually defined. They're not implied. All right, what do I mean by that? I mean, there's actually a connection from one row in the database to a corresponding row or rows in another database table. One thing I don't know if we mentioned last time is the idea of a primary key. And a primary key is a column or combination of columns that uniquely identify a row. And the rules for a primary key are that it has to be unique. In other words, there can't be two members of that entity that have the same value for it. And every row in the database, every row in that entity, every member of that entity has to have a value. For example, if we think of student number would be an example of a primary key. Every student has a student number and they're all unique. Can you imagine the chaos that would ensue if two people had the same student number? If those two students enrolled in class, you wouldn't know who enrolled in that class. Student 123 or 123 in that class, right? Doesn't make any sense to talk about it that way. Now, that's pretty much what we're going to talk about as far as single tables. Where databases get really interesting is in the terms of relationships between different entities in the table. And there's three basic kinds of relationships. And it's typically, and again, there's variations of these, We're only going to be interested mainly on the level of whether they are a one-to-one relationship, a one-to-many, or a many-to-many. There are like one-to-many optional and, optional becoming mandatory. And there's all kinds of qualifiers for these. But in the face of things, when you get down to basics, there's the three kinds of relationships: the one-to-one, the one-to-many, and the many-to-many. That is called the cardinality of the relationship. Usually if we draw an entity relationship diagram that shows, cleverly enough, the entities and the relationships between those entities, we indicate a relationship by drawing a line between the two entities. And then there's a number of ways that we can show the cardinality of the relationship. For example, We're going to talk about the most common relationship first, and then we'll talk about the other two. Most common relationship is a one-to-many relationship. And that would be maybe between professor and department. At least here at Lorain Community College, each professor is a member of a department, right? There's a relationship between professor and department. And that relationship is a one-to-many relationship. But one-to-many going in what direction? The way that we look at that is we look at it going both ways and see where the many side of it is. One professor only has one department. And at Lorain Community College, that's true. To my knowledge, there are no professors that work in two different divisions. They have one home department that they belong to. Even if they were to teach a class in another division, they would be, still belong to their home division. So one professor has one department, but one department has many professors. So this is a one-to-many relationship between professor and department. Now again, you really have to look in both directions to determine it. If you look only in one direction, you're liable to get confused and think it's one of the other two kinds of relationships, either a one-to-one or a many-to-many. So you have to look at both directions. Now, that's all good to draw it that way, but how do we represent that in the database? We represent that in the database by having what's called a foreign key. In the professor table, there's probably something called the professor ID, right? Like the student number, except it's the professor number. And there's probably a department ID in the department table. And the department might have the department name, might have where their office is located. It may have other pieces of information. But these two are the respective primary keys. A professor might have their first name, their last name, and so on. Now, to implement that relationship, you have what's called a foreign key. And I'll designate that by using two asterisks. A foreign key is where you have an attribute or a column of one table that points to the primary key of another table. Let me give you a for instance. If we had the following in our department table, and department 1 was engineering, business, and IT. Department 2 was health sciences. Department 3 is social sciences. Department 4 is arts and humanities. And I think I'm missing a couple, but That's pretty much most of the departments here at Learning Community. If we then have in the professor table, we have a professor ID, and maybe professor 1 is Mike Zellers. His office is BU 211J. His phone number is extension 47. What is my extension number? It's embarrassing. Let me look it up. Probably should know that, huh? Don't call me on the phone, by the way, because I usually don't get my I usually don't answer my voicemail. It's much better to email me instead. I usually don't get the voicemail until after 4796. I knew I'd remember it. And last but not least, there is a column that's a foreign key to department ID. Now, when a foreign key is set up, you cannot have a value in the foreign key that doesn't match one of the values in the related table. So in other words, let's assume these are the only 4 departments. I would not be able to insert a row into the database that would have a department ID of 5. The insert would fail because of an integrity constraint violation. That's a good thing, right? We don't want employees working or professors working for non-existent departments. That's a recipe for bad data. Everything's going to be screwed up then if you do reporting or anything like that. And that's how things were in the old days with plain old files, where we didn't store the relationship and we didn't have things called foreign keys. But this is actually, if you build a foreign key in the database, you cannot put in a value that doesn't match. So you'd have to put one of those in. Now, depending on the particular column, you might be able to enter nothing in the department ID. That might be allowable. All right. Trying to think of a case where that would be with faculty and department. That probably isn't a good case for that, unless there was a faculty person that they hired and they weren't sure where they were going to assign them yet. Maybe they'd assign them, maybe they did, software stuff, and they might assign them to business, or they might assign them to math and sciences. I think that's one of the other departments. But eventually they're going to have one. That's what I meant where I said or optional becoming mandatory. In other words, later on it would become mandatory. So I put a 1 here. All right. So there's a foreign key built that's going to match up the 1 here with the 1 here. If we have second employee, second professor, arms is also in 2. We have a nursing professor. They would be in department 2, and so on down the line. Now, you couldn't add it unless it had a valid department ID. You can't change it to an invalid department ID. So if I go in the database and try to change this to 12, it's going to fail and won't let me do it. Now, something interesting comes along with deletion. All right? Because what if I deleted this department? You have 2 choices with the foreign key. either you delete all the professors that belong to that department, or you don't let a department to be deleted as long as they have professors that belong to them. That's on a case-by-case basis. For example, you have an order and line numbers. If you delete the order, you're probably going to delete all the line numbers, or line items associated with that order. But in this case, I probably wouldn't delete all the professors. I'd probably prohibit deletion of a department as long as there were professors that belong to that department. I'd give a chance for you to deal with the professors first, maybe transfer them into another division or something before I would go in and allow you to delete the department ID. So this is a one-to-many relationship. And on a one-to-many relationship, the entity on the many side that's the one side. It's the many side. The entity on the many side points to the entity on the one side. So we would not have a professor ID in the department table. Why not? Well, because a department can have multiple professors. There isn't room for just a single ID in there. But because a single professor can only belong to one ID, or one department, we can put the department ID of that professor in there. So that's an example of a one-to-many relationship. Again, going back to our drawing, that is shown like this. Now, sort of a rare relationship would be the one-to-one relationship. It's almost hard to think of examples of a one-to-one relationship, but I think I have a couple of them. What about the relationship between dean and department? Now, a dean is the dean of one department, and a department only has one dean. First of all, we would verify that that's true. You know, is there a possibility to have co-deans? If so, then it would be a one-to-many relationship. A lot of times, upon further scrutiny, you find out what you thought was a one-to relationship is really an example of a one-to-many relationship. We'll get to an example of that in a minute. So how do you implement this? Well, you can do either way. I would suggest you don't do it both ways, though. You could put a dean ID as a foreign key in the department. But you'd also have to put a constraint to make sure that that is unique. Fortunately, we're rarely going to see one-to-many or one-to-one relationships. In fact, a lot of times, if you scrutinize them, you find that they're not really a one-to-one. They're a one-to-many. We try to think of an example of that. Well, let's talk about on campus the relationship between coach and an athletic team. Relationship between coach and team. Now that might on the surface look like a one-to-one relationship, right? A coach coaches one team, a team is coached by one coach. You'd have to look at that more closely though, because maybe it's possible to have co-coaches of a team. You'd have to find that out. Or maybe it's possible for a coach to coach more than one team. Like, for example, they're the basketball and golf coach. Certainly a possibility. Therefore, if you look at it more closely, you might find that maybe, well, yeah, a coach actually can have multiple teams. So what you thought was a one-to-one relationship actually turns out to be a one-to-many relationship. Now, I said that the most common relationship is a one-to-many relationship. And here's why. Because the third type of relationship is a many-to-many. Again, this one you have to look at closely. Make sure it's truly a many-to-many and not just a one-to-many. An example of that might be the relationship between students and courses. Clearly, there's a relationship between students and courses, right? Let's look at the cardinality of that relationship. The cardinality of that relationship says that one student can have how many courses? Well, they could have multiple, right? Now, in database terms, the only numbers that are important are 0, 1, and many. So, you might think a student, well, students typically take 4 or 5 courses. Doesn't matter if they take 4 or 5 courses. You're not going to build your database to hold 4 or 5 courses per student. You're going to build it for the database to hold many courses for the student. So one student can have multiple courses. Now, if we flip this around, how many students are in a course? One course can have how many students? That is also many. So this is what is called a many-to-many relationship. Now, here's the thing about a many-to-many relationship. You can't directly implement a many-to-many relationship in a relational databases. Because if you think about it, how would you do that? Would you have courses? Would you have slots for different courses in the student table? Would you have slots for different students in the course table? You couldn't simply have a course ID in the student table because the student can take more than one course. Likewise, you couldn't simply have a student ID in the course table because a course can contain multiple students. So, many-to-many relationships become resolved to 2 one-to-many relationships. We're going to call this table student course. That's what I usually do when I create a table that's an intersecting entity between 2 entities. You can also call it something like enrollments, if you'd rather. And a student can have many of these enrollment records, but each enrollment record only relates to one student. Likewise, a course can have many enrollment records or student course records, but each one of these records can only have one course. So it's like a cross-reference table. Show you what I mean here. Let's say our course table has a course ID and the name and a number of credit hours. So course ID is 1. The name might be CISS243. And that's 4 credit hours. And maybe there's a description, web database. Course number 2 might be CISS232. 3 credit hours, client server. Course number 3 might be biology 101. 3 credit hours and it's just called biology. And so on down the list. Now we might have a student table that has its own student ID. And has these students in it. All right. Might have some other information about it, their email address, their phone number, and so on. Maybe George is taking all 3 of these courses. Maybe Paul is only taking bio. John is only taking bio and CISS 143, and Ringo is taking CISS 232. Well, in our student course table, you can do this several ways. But one way is to have a student ID and a course ID, and the combination of those 2 is the primary key to the table, which means that the combination of those 2 fields have to be unique, not each field individually. So George takes this course, George takes that course, George takes that course. I don't remember what I said Paul takes, but we'll say CISS 243. John takes CISS 243 and biology, and Ringo takes CISS 232. We can't put a course ID in this table. It's not going to work because there's multiple courses that a person can take. Therefore, we build an intersecting table. It's like a cross-reference table. If I want to know what courses this student takes, I look for all the student IDs of 1. And then I get the course IDs and I match that up with the course to get the course name, the course description, and the credit hours. Now, and these also would be, these 2 together would be the primary key, and individually they'd be foreign keys. So I couldn't put in student 4 is taking course 88 because there is no course 88. You just would not be able to add that to the database. Get an error. Now again, you would set up whether there's cascading or restricted deletes. If I delete a student, for example, maybe I want to delete all their course records. So I make it cascading deletes. So the process of database design is looking at your entities and deciding, so you brainstorm, you think of all the entities that exist in an organization. Like I said before, a college has students, has professors, has courses, has majors, has classrooms, has equipment, has administrators, has departments, and so on. You brainstorm to get a list of those entities that they have. Then you look to see the relationships, and you try to define the cardinality of the relationships, and then you fill out all the attributes. For a student, what is it that we want to be able to have? Well, we certainly need their first name, their last name, their student number, and so on. What's going to be the primary key? Well, their student number will be the primary key. A lot of times, just a plain sequence number becomes the primary key. Auto number, where the next row in simply gets the next number. So if we added a course, it would just get added with a course ID of 4. All right. So we've done all that. What have we done? We have defined our entities, defined the relationships of the entities, defined the keys and foreign keys, define all the attributes for the entities. Are we done? Probably not. We want to go through a process that makes sure that we've done that correctly. And that process is known as normalization. Do that. I'm going to type in Word. Normalization is a process of trying to guarantee that we've defined all the entities and we have the relationships correct. It's a series of tests you put the database through in deciding, have we identified all the entities? Have we identified the relationships correct? And I'm going to show you this example. And this is not an uncommon one. But an example where you have a spreadsheet that has rows of data in it, and someone wants to make a table from it, or a set of tables from it, a relational database. All right. The first normalization rule says each entity, each table contains an entity, has a key, and the big one, no repeating fields. Well, let's look at our example here. Yeah, this table is an entity about one thing. It's about computers. There we have a computer ID. That's the primary key. Are there repeating fields? There are. There are application and code 1, application code and name 1, application code and name 2, application code and name 3. Now, this is a pretty absurd situation, right? Because any computer is going to have more than 3 applications, but bear with me here. What is wrong with this strategy? Well, 2 things are wrong with this strategy. One thing is just what I named right there. What if you had a computer that had 4 applications? What do? There's not space for that. Secondly, if you wanted to find every computer that had a certain application, you'd have to look in 3 different places for it. Now, if we made 10 applications per computer, there'd be 10 different places we have to look for it. And that's not good. So when you have a case of duplicate or repeated fields, what you typically do is you take the table, break out those repeating fields, and make a new table for them. So what we're going to do, we're going to break out this. To get rid of all these from our main computer table. And we're going to create a second table whose key is computer ID and application code. So computer and application name. So we'd have computer 1, computer 1 has Microsoft Office. Computer 1 also has Visual Studio. I don't remember the original data I had, but maybe computer 2 has Microsoft Office and Visual Studio. So this is the first step of the normalization process. We're not there yet, but we've gotten rid of the repeating fields. That's a big win, right? Because what if a computer has 10 applications on it that we're interested in? There's simply 10 rows in this table. What if there's 100? There's 100 rows in this table. So there's no limit. Again, we're not interested in specific numbers. We're interested in 1, 0, or many. And this will accommodate many. Now, the next thing is we look for fields, and I hope I'm doing this in the right order. I think I am. No column should depend on part of the key. What do I mean by that? Well, let's look at this example. The key to this table is the combination of the computer ID and the application code. The application name only depends on what the application code is. In other words, on computer 1, you have Microsoft Office. MSO means Microsoft Office. MSO means Microsoft Office for every computer. Therefore, they shouldn't be repeated for each particular computer. The application name depends only on the application code. Solution for that, we break this out into another table. And then get rid of this column. Now, we look to see, so that's the second normalization rule. We look for things that depend on only part of the key. Third rule is no column should depend on a non-key item. Well, we're okay with these two tables. What about this table? Well, the name of the building depends on the building code. Therefore, I'm going to create a building table that has the building code and the building name. And I'm going to get rid of the building name in this table. Likewise, the room description depends on the building code and the room. So we're going to create a room table that's going to have building code, the room number, and the description. So BU 106 is the open lab. So on. So now when we're done, we started with one giant entity that actually contained multiple entities. By following these normalization rules, we've split it down to where we have several entities. But the good thing is for each of these entities, there's no repeated data. There's only data that points to other data. We want to know the description of this computer's location. We take the room ID or the room code and building code, look in this table and get it. We want to find out what software computer one has. We look through this table and then use the application code to find it there. So we've broken down and identified all of the entities that were hiding in that one entity. And that's really what normalization is. All right, next week is going to be an exciting week. All right, it'll be our first chance to merge the two topics of this class. Creating ASP.NET web pages using Razor pages and database stuff. So we're going to run through, we're essentially going to run through a tutorial that it's your job to complete and turn in the completed files for. So, and then you have to alter the contents of the tutorial a little bit to add something. And we'll talk about that next time. But we're going to actually create a website that we can use to maintain and display data from a database. So it's pretty exciting. After that, that's what we're doing the rest of the semester. All right. And it's not too early to start thinking about your project in terms of what database you want to maintain and so on, and running it past me. All right, that's all I had for today. Are there any questions? All right, I will see you in lab, or I will see you next week.